In this video, we are going to talk about eigenvalues and eigenvectors of a square matrix A. We say that a scalar number lambda is an eigenvalue of A if AV is equal to lambda V. That is, the product AV is a scalar multiple of the vector V, where V is now called an eigenvector of A corresponding to the eigenvalue lambda. Now it's important to specify that this V must be a non-zero vector. Otherwise, if we allow V to be the zero vector, well, since A times the zero vector is lambda times the zero vector for all scalar numbers lambdas, that would mean that every real number would be an eigenvalue of A. Well, that's not what we want. So we must specify that V is the non-zero vector of Rn. So how would we find the eigenvalues of a square matrix? Well, we know that eigenvalues satisfy that AV is equal to lambda V for some non-zero V from Rn. Well, that is the same thing as saying that it's equivalent to saying that AV minus lambda V is the zero vector for some non-zero vector from Rn, or equivalent to saying that A minus lambda times the identity times the vector V is 0 for some V which is not equal to 0 from Rn. Well, this here says a little bit more to us, so let's think about it. If A minus lambda I times V is the zero vector, that says that this V is inside the null space of A minus lambda I. Well, don't forget that V is not equal to the zero vector. So that tells me that the null space of A minus lambda I is not equal to the zero vector alone. So that says something about A minus lambda I. Well, it says that it's not row equivalent to the identity matrix. There are, if we reduce this to the row reduced echelon form, we would find some columns of that row reduced echelon form with that do not have pivots. So that's equivalent to saying that A minus lambda I is not row equivalent to I, to the identity matrix. That's the same thing as saying that A minus lambda I is not invertible. In other words, is singular. It does not have an inverse. Well, we know from the properties of determinants that a matrix is not invertible if and only if its determinant is equal to 0. So the determinant of A minus lambda I must be equal to 0. So that gives us a way of finding these lambdas. Basically, what we need to find is the determinant of A minus lambda I, set it equal to 0, and solve for lambda. So to find eigenvalues of A, we need to find the roots of the determinant of A minus lambda I. So we will see in the following example that the determinant of A minus lambda I is actually a polynomial, and we call that polynomial the characteristic polynomial of A. So let's start with an example. So I will get A to be the matrix 1, 2, 0, 2, 1, 0, negative 1, 2, 3. And we need to find the eigenvalues of A. So in my solution, I would need to find the matrix A minus lambda I first. So that is the matrix A and from this I need to subtract the matrix I multiplied by lambda. So that's lambda along the main diagonal and 0 everywhere else. Well, let's find this. This is basically A, but from the main diagonal of A we will subtract lambda. So we would have 1 minus lambda, 2 minus 1, 2, 1 minus lambda, 2, 0, 0, and 3 minus lambda. The next thing we need is to find the determinant of this matrix. So the determinant of A minus lambda I, well, I will expand along the third row because it has two zeros. So plus, minus, plus, minus, plus 3 minus lambda times the determinant of the matrix that we end up with when we remove the row and the column in which 3 minus lambda is in. So 1 minus lambda, 2, 2, 1 minus lambda. Well, this is a 2 by 2 matrix, so the determinant of that is the product along this diagonal. That would give me 1 minus lambda squared minus the product of this diagonal. Now, what I have is a difference of squares, so I can factor this to 1 minus lambda minus 2 times 1 minus lambda plus 2, and this gives me 3 minus lambda. 1 minus 2 is negative 1 minus lambda, and 1 plus 2 is 3 minus lambda. So this is a polynomial of degree 3, and we see that this polynomial is equal to 0 if lambda is equal to 3 or lambda is equal to negative 1. So A has two eigenvalues. Lambda 1 equal 3 and lambda 2 equal negative 1. In the next video, we're going to talk about how to find the eigenvectors of eigenvalues.